Okay, so in this problem, it's a problem with a person jumping from a certain height. So here's the person, and they're jumping from a certain height down, and the height which they are going to jump, let's say, is called h. That's the answer which we're looking for, is the h. Now once they hit the ground, let's extend the ground here, they're going to kind of look like this on the ground. And then once their legs touch the ground, they're going to be lower down on the ground, and their legs are going to bend. So in terms of the distance that the person goes once their feet touch the ground, it's 0.6 meters. Okay, so they've jumped down from some height, they're falling, their feet just touch the ground, and then it takes them another 0.6 meters to come to a stop. Okay, so at this point, their velocity is not 0, but at this point, their velocity is 0. Question is, what is that velocity? Well, in order to find that out, we can use a little bit of conservation of energy. Now, that's one way to do it. But if you say the initial energy is equal to the final energy, going from here to here, then initially the person jumps from rest, so they just have gravitational potential, and then finally at the bottom they have kinetic energy. This is not when they come to a stop. This is just when they're touching the ground. So the m's cancel out and take the 2 up there, and so the final answer is 2gh equals v. Okay, now we can put that in here. So that's 2gh, and by the way, this velocity is going to be down. Okay, so technically, I guess we should put a negative in there. Now, what does the problem give us? Well, it gives us that the person's leg has a bone in it, and the cross-sectional area of the bone is equal to 3 times 10 to the power of negative 4 square meters. In addition, we know that the person's mass is 60 kilos. What else do we know? Well, we also know that the pressure to make the bone break is 170 times 10 to the power of 6 newtons per meter squared. Now, using the pressure equation, which is pressure is equal to force over area, we should be able to find the force that's going to break the leg simply by multiplying P times A, which is 170,000 power of 6 Newton meters squared multiplied, that's 100, multiplied by 3 times 10 to the power of negative 4 square meters. And that gives us 51 times 10 to the power of 3 newtons. That's how much is going to break the leg. So let's write that down as F max. Okay? Now, if we look at the body of the person at this point, let's draw a free body diagram here. At this point, we've got force going down and a force going up. And the upwards force is going to be the normal force, and the downwards force is going to be the force of gravity. Therefore, if we do summation of the forces is F net, we've got Fn, which is up, so is positive, minus Fg is equal to F net. Now, why is that important? Well, because between this position and that one here, there is a acceleration that is going on, okay? And we all know that, let's change colors here again, we all know that F net equals ma. And we also know that we have a kinematics equation. V final squared is equal to V initial squared plus 2a delta d. Now the reason why I have this equation is because I need to be able to find the a. Now F net, I can substitute. I can say F net is Fn, which is the normal force, minus Fg from here. That's F net, so I can equal that to ma. Fg, that's easy. Fg is simply mg. Fn, what's the normal force? Well, guess what? The normal force is the force that the person's legs exert. Therefore, the normal force is F max. Hence, I can put 51,000 here. Made a mistake here. Let's just correct that. 51 times 10 to the power of 3 minus mg equals ma. Problem is I need a. I don't have a. I can find a from this equation simply by saying a equals v final squared minus v initial squared all over 2 times delta d. Now, what's my final velocity? Well, my final velocity is here, and my initial velocity is here. Okay, so I'm going to go acceleration 0 minus root 2gh all squared all over 2 times delta d. That's just going to equal now, yeah, it's not really important. I mean, technically speaking, I suppose we should put a negative in there for the velocity because it's down, but not a big deal because we're going to square it. So we're going to get negative 2gh on top because the square is going to cancel out the square root, and on the bottom we have 2 delta d. 2's cancel out. And by the way, delta d was negative 0.6. So we've got gh all over 0.6 for the acceleration. Now, if we plug it back into here, we have 51 times 10 to the power of 3 minus mg equals m times gh all over 0.6. By the way, hey, I made a little kind of a boo-boo here, and that is this delta d is actually equal to negative 0.6. Okay? So let's put it there. Okay? Now you're wondering, why that is. Well, it's a loss of altitude. That's why, delta d. So, and by the way, if you're wondering, does that mean if the person, when they're accelerating from here to here, does that mean the acceleration is positive or negative? Well, remember, up is positive, okay? So they're not accelerating down, they're accelerating up. So how can the acceleration be positive? It's a positive acceleration. But how can it be positive if we have a negative? The answer is this g here is negative 9.8. So the negative and the negative cancel each other out, so you get a positive value. Okay? That's one way to look at it. Now, our objective here, let's not forget, is to find h. Okay? So let's solve for it. So what I'm going to do is I've got negative 0.6 times 51 times 10 to the power of 3 minus 60g and then divided by 60g. Now, one thing, this is actually a negative 9.8. Okay? And I know what you're wondering. Is this one a negative 9.8? It's not. That's a positive 9.8. And the reason for that is because this g came from the free body diagram here, where FG is mg, and we're already taking into account that it's negative by having an arrow down, and that arrow down actually caused this negative sign here. So let's work it out. What do we get for h? And by the way, h is equal to all this. So let's get our trusty calculator. And let's go 0.6 negative, enter, 50, well, actually, let's start from the inside here. Let's go 60, enter, 9.8 times. And then let's change sign that. And then let's go 51E3 plus that. And then multiply that by 0.6. Negative times, and then divide that by 60, and then divide that by negative 9.8. And the answer we're getting is 51.4 meters. So that's the height from which the person can fall by imposing the largest possible force without breaking the leg. Personally, I think it's a little too large to be realistic. But hey, that's the end of the problem. Thanks for watching.